Should we care about space weather? My name is Jennifer Alford and I'll be your moderator today, and we're going to meet our scholars in just a minute, but first I want to give you a little bit of an idea of what we're up to here today. So this is one of a series of webinars that we're presenting where University of Calgary scholars share some of their information from their research with us. We are taking questions. We'd love to get your questions. We may not have time to get to everybody's questions, but if you could if you have some questions, just type them in that little box there, and we'll do our very best to try to get to as many questions as we can. We also have a lot of resources, so don't forget to click the link there to find out some of the resources that our researchers will be talking about. If you happen to be on Twitter, please keep the conversation going with the hashtag #ExploreCalgary. And at the end, we have a little very brief survey that we'd ask you to take a minute to fill out so that we know what you think of how we're doing. Okay, enough about that. So now let's meet our scholars. Eric Donovan is a professor in physics and astronomy and the Associate Dean Research and Graduate Studies in the Faculty of Science. Hello, Eric.
Hi, Jennifer.
And we have also Emma Spanswick. Now, Emma is the Associate Director of the University of Calgary's Auroral Imaging Group and an Adjunct Assistant Professor in the Department of Physics and Astronomy. Emma, welcome.
Thank you.
Now, I wanted to start with you today and ask you, first of all, the name of the webinar. Why should we care about space weather?
Well, first I would say, great question. 50, 60 years ago, we didn't really care about space weather. And as society has grown, as our infrastructure has grown, we started to notice the effects of space weather. And that's something we'll get to a little bit later as Eric will talk about space in general. But what we've noticed when we've grown, we've noticed corrosion in pipelines, we've noticed the effects on GPS signals, the effect on HF radio communications, even something such as directional drilling in the Alberta oil patch. We notice the effects of those. And I think we'll come back to that, and I'll let Eric dive right into space, and then we'll get to the effects of space weather.
Okay, great. Eric.
Okay, well, thanks Emma, thanks Jennifer. And so first of all, people may know this already, but 60 years ago, I think it was last Thursday, Russia launched the Sputnik satellite, and that really was the beginning of the real space age. And the U.S., this created a crisis for the U.S. because this was an important strategic thing. And the U.S. decided to launch something as soon after as they possibly could. Unlike Sputnik had a radio transmitter on it. Unlike Sputnik, this first American satellite had a Geiger counter that was put on by a guy named James Van Allen from Iowa. And I'm just, I'm showing you a picture here of the Time magazine, which was from that time period where James Van Allen was named the Man of the Year for Time, and Werner von Braun and Carl McElwain and James Van Allen are holding the rocket up, the satellite up below there. And what they discovered with this Geiger counter was the Earth's radiation belts, and it was, which is very, very high energy charged particles that are trapped in the Earth's magnetic field. And that was really the beginning of people realizing that this region of space around the Earth that we call geospace, neurospace, or the magnetosphere, that we refer to it in different ways. It's the outermost part of the Earth's environment, and it's a very, very dynamic environment. And that's what I'm going to talk about just in the next few slides. We've got a lot of slides, but I go through them very quickly. So
this was sort of the beginning of figuring out that there is such a thing as space weather.
It was the very beginning, because people really thought, initially that it was vacuumed up in space, and it was really a bunch of clues that came in the 1950s and 1960s that it wasn't, and that the Earth's magnetic field really captures lots and lots of charged particles, and that they do lots of things in the Earth environment that are very, very impactful on our upper atmosphere, and it turns out on our society. And so what I'm showing here is a picture of a total eclipse of the sun, not the last one, not the most recent one, but you people will have seen this, and you see around the moon, you see these tendrils coming out from the from the sun, and that actually is the sun's corona. It's the outermost part of the sun's environment. It's its upper atmosphere, and the corona is, the surface of the sun is about 5,000 degrees Celsius, and the corona is about 2 million degrees Celsius. It's heated from below. We still don't really know exactly how that works, but the corona, it's so hot that the gas is expanding up and out throughout the solar system constantly. And so that's why you see those tendrils that are being drawn out with the solar wind. And I'll come back to that. But that solar wind is really the engine that powers space weather. Now, just going forward, you know, you have the surface of the sun, you have this corona and the solar wind, and then we have this thing that, I'm not going to get into details about this, but in space physics we call it the frozen-in condition. And simply put, what it means is that plasma, this ionized gas at the solar wind, carries magnetic field with it. And there's physical reasons why plasma can't move from one magnetic field line to another magnetic field line, and so it just carries this magnetic field outwards with it. But then if you look at it, if you think about that, the Earth has an intrinsic magnetic field that would look like a dipole, the field of a dipole, if it weren't for the solar wind. And when the plasma gets up near the Earth's magnetic field, that plasma can't move into the region of the Earth's magnetic field because of this frozen-in condition. And what that does is it compresses the magnetic field on the day side of the Earth and drags the magnetic field lines out to really long distances behind the Earth, you know, millions of kilometers, way past the moon. And it creates this windsock-shaped thing that we call the magnetosphere. And this is just one of the sort of a scientist schematic of the magnetosphere. All I'm going to say is there's different regions. They have different kinds of plasma that come from different places. Some of the charged particles come from the Earth's upper atmosphere. Some come from the sun. Some come from the moon. They just come from wherever they are. And then things happen to them inside the magnetosphere. And so,
okay, and they don't necessarily mix, as I think you were saying a minute ago, right?
Well, yeah. And in fact, what you're seeing is, you know, the different regions are plasma from different places, right? And so, and the magnetosphere is a very dynamic environment. There's a lot of physical processes going on. A lot of those processes generate cumulatively this thing that we call the aurora, or the northern lights. And I'm just showing a picture here from an imager that is at the University of Calgary Heritage, actually, that took this image of the global aurora over the northern hemisphere, this ring around the north magnetic pole. It's there 24 hours a day, 7 days a week. It's dynamic. It gets bigger. It gets smaller. It gets brighter. It gets weaker. You know, and it has all kinds of structure and dynamics. And we'll come back to that, because this is actually the scientific tool. My scientific tool is to use the aurora to study what's going on in the magnetosphere.
They're more than just a pretty face.
Yes, absolutely, but they are quite beautiful. And so if you look at this figure, I mean, basically the Earth has a magnetic field, and anything in the solar system that has a magnetic field gets a little magnetosphere around it. So what I'm showing you here is our schematics of Mercury's magnetosphere, Earth's magnetosphere, Saturn's magnetosphere, and Jupiter's magnetosphere. And if you were able to see Jupiter's magnetosphere, it would be far and above the biggest thing in our solar system by a lot. If you could see it with the naked eye, it would take up all the night sky sometimes if you were to look at it from here. So it's just a huge thing in the solar system. But you know, we tend to focus here on the Earth's magnetosphere, but every magnetosphere also leads to aurora. And so I'm showing you that picture of the aurora that I showed earlier from orbit around the Earth. But these two bottom images are Hubble Space Telescope images of the aurora on Jupiter and on Saturn. And you know, and we've learned a lot about the aurora by looking at the way the aurora is different in these different planets. You know, and one of the things I've always like to comment on is that we have better global images of the aurora for Jupiter and Saturn than we do for the Earth. And that's because turns out a $10 billion telescope, which is the Hubble, you know, looking from this far away, does a better job than a $1 million telescope that's looking from 50,000 kilometers away. And so I keep arguing for 10 billion for this. But
chances are we have more people on the ground on Earth taking pictures up above, however.
Absolutely, and I will show some. I will show some. And so the idea of, you know, space weather, you know, if you think about weather down here on Earth, we've been studying weather down here on Earth for centuries, you know, and we've been studying space weather for decades, and it's actually a bigger system and in some ways a more complex system, and the physics is new physics, a lot of the stuff that drives what's going on. And so this is actually a focus. Understanding what's going on with space weather is actually a huge scientific focus for the global research community. And I'm just showing you here, the left-hand side is a schematic of all the satellites that are presently either sitting at the Lagrange point between the sun and the Earth or orbiting the Earth that NASA is flying right now to study what's going on with space weather. And on the right-hand side, just a schematic showing 3 satellites that the European Space Agency has in orbit right now called SWARM. And those are actually carrying instruments from the University of Calgary that measure the electric field around these satellites. And the point I like to make with this is that the U.S. government, the European Space Agency, England, Japan, and other nations cumulatively have about $20 billion of assets in space right now trying to understand space weather. So this thing is recognized as strategically important to big economies. And it's really an exciting time for people like Emma and I because this is really the discovery phase for our field. And we're plugged really right into this with the stuff that we do that we'll talk about a little bit here. And then finally, I just want to show this movie, and it may play well for some of you, I hope it does. And this is actually taken from the European Space Agency's SOHO satellite, which is a space probe, which sits at the Lagrange point between the sun and the Earth, which is where the sun's gravity just balances the Earth's gravity. It just kind of orbits that place, and it's been there for, I think, 30 years. And what you're looking at is 1 month of data looking at the solar corona and looking at the sort of formation, the birth of the solar wind. And what you can see is it's very dynamic, and those dynamics are, so the solar wind itself provides the energy for space weather, but the dynamics also create a lot of the havoc that we would call space weather. And again, I'm not trying to teach people here. I'm not going to go into the data in any great detail, but I'm looking at some data from one of the solar wind spacecraft. I think it doesn't matter what spacecraft it's from, actually. And all I really want to show you is that place with the gray bar there, and you're looking at hours on the bottom. And then you can see that the solar wind had a dynamic pressure of 1 nanopascal. And then in a few minutes, it increased to 10 nanopascal, right? And so that doesn't really matter. It's just that the solar wind was blowing a lot harder at that point. And so if you look at the next slide, what happens is, this frozen in condition is what creates the magnetosphere. But the compression on the front side of the magnetosphere is really because of the pressure of the solar wind. And so if you push harder on the magnetosphere, then the magnetosphere gets smaller, and then that drives all kinds of wild stuff. And the next graph is just showing you the magnetic field traces from the west coast of Hudson Bay on the top plot, and just some auroral luminosity measured by what we call a photometer. And that kind of wiggle in the magnetic field and the sudden brightening in the aurora is what happened when that compression in the solar wind hit the Earth's magnetosphere. And this is and this is what I call an externally driven space weather event. And then we also have what we would call internal dynamics in the solar wind. And I'm sorry, these images are off to the left. I meant them to be centered on this. And then what I'm showing you here now is from what we call an all-sky imager, and that is a camera with a fisheye lens that's just pointing straight up. And this was in Athabasca, and back in 2004, and 2 colleagues of ours were working in a field behind the Athabasca Geophysical Observatory. And the way they described what happened here, you're looking at about maybe 600 or 800 kilometers across the sky if you think about where the horizon is at 100 or 200 kilometers altitude. And you can see that there's an auroral arc, what we call an auroral arc, on the southern horizon. So this is actually a time when the aurora is moved quite equatorward. It's equatorward of Calgary there. And it's just sitting there, but it's very quiet and not really doing very much. And they described it as being basically close to subvisual. And
meaning that you almost can't see it?
Yeah, it'd be just sort of a little bit of green on the horizon, and that's it, right? And then so over the course of the next 2 minutes, I'm just going to play this for you one slide at a time. The slides are separated by 10 seconds. Over the course of the next couple of minutes, what you see is the aurora getting brighter and starting to move, we call poleward, and starting to fill the sky. And so basically, after about 2 minutes have gone by, you've gone from a situation where the aurora was subvisual, or close to subvisual, to having aurora that's horizon to horizon to horizon to horizon. Very bright, casting shadows. They swore that they probably couldn't, but they thought you could probably read by this light. It was so bright. And this has happened in just really, truly, just a matter of seconds. Okay, and so I'm going to come back to that, but that's a different kind of space weather event because it's caused by an internal thing that goes on in the magnetosphere without a change in the solar wind that made this happen. And so there's really external things and internal things. Now I'm going to just talk a little bit about kind of why this matters for Canada. And I often argue that Canada is the nation on Earth that is the most vulnerable to space weather, and there's a reason for that. That a lot of the space weather activity has to do with the processes that couple the magnetosphere with the ionosphere, and a lot of that coupling goes along with the aurora. And what I'm showing you here is a figure that actually Emma made like 15 years ago or something like that. And on the right-hand side, what you see is this auroral oval. Well, it typically sits between about 65 and 75 or 70 degrees geomagnetic latitude. And so if you look at those geomagnetic latitudes, you can see that almost all of the readily accessible land on the planet that's under the auroral zone is in Canada. And that includes the southern hemisphere, too, for the aurora australis. And so these things, these events that affect the atmosphere and affect technology, they are felt most keenly at these auroral latitudes. And also that means that so Canada is really space weather vulnerable. The flip side of that is that Canada has the land under the aurora. And so we're not the U.S. and we're not the European Union. We're not the European Space Agency. And these satellites that are probing this science, these are billion-dollar satellites, and we just don't do that, right, in Canada. We don't have that capacity. We have the Canadian Space Agency, and they're keenly interested in this. And for a long time, Canadian Space Agency and other agencies in Canada have been investing in putting stuff on the ground that we use to look at the aurora. And that is sort of our contribution to this global effort. And so we get for a few $1 million, and I'm not saying that's not a lot of money, but I'm saying it's not $1 billion. We get for a few $1 million a basically equal seat at this space weather science table. And people all over the world use the data that we produce, and in particular here in Calgary, where we are, I mean, without any hesitation, I'd say we're the best, group in the world in terms of doing this kind of observation of the aurora from the ground. And so we are plugged into NASA missions and European Space Agency missions and so on. And it's fun, it's exciting, and it's a really inexpensive, well, I mean, again, relatively inexpensive way for Canada to be a global player in this scientific arena. And then on top of that, the aurora is, as you mentioned before, I mean, it's more than a pretty face, but it is a pretty face, right? And I'm just going to show you some photographs of the aurora that people from what's called the Alberta Aurora Chasers have on their Facebook page, which I strongly recommend people join. And if any of you are out there, I'm sorry I didn't credit your names on these, but we'll, you can yell at me later. And
so these are folks who go out and take photos at night.
At night, yeah. Okay. And so this is for me. We look at the aurora as a scientific tool because we use it to probe what's going on in the magnetosphere remotely, but it's also this phenomenal, stunning, beautiful natural phenomenon. And if you've ever been up north and, in a place like Yellowknife or Whitehorse or even Athabasca, and you've had the opportunity to be out in this kind of northern environment and see this and experience this, I always say that the first time this happened to me, it sort of changed my view of the night sky, okay? And so but that's back to the idea of space weather. I'm going to go very quickly through this. These are two figures from a proposal for a NASA mission that was written back in 2002. And I was involved with the writing of this proposal. It was led by a guy at Berkeley. And, it's a long story. It's a fun story to tell, but I'm not going to tell it. But the fact is that in 2003, this mission, which was to determine what that thing that my friends saw in the Athabasca, that explosion of light, that we call a substorm, and it happens in the magnetosphere, and the goal was to determine what causes that. And we decided to take 5 spacecraft, NASA spacecraft, adding up to $200 million. NASA paid for that, it's not Canadian money, okay? And to string those 5 spacecraft out in a line down the Earth's magnetotail. And then at the same time, I'll get to what we do with the ground-based instruments, and they would look with these 5 spacecraft and see where in the magnetosphere this initiated. But the problem is, the magnetosphere is very big, and the guy who runs the Themis mission is a friend of mine, but he gets upset with me when I say sometimes that the biggest discovery from Themis is that the magnetosphere is really, really big, because we found out some things that we now have to look deeper. But those 5 spacecraft are in a line, and it's a 3-dimensional region of space. And so we had to know when there was a disturbance, if that disturbance was kind of along that line of those 5 spacecraft. And so the answer to that was to cover Canada and Alaska with cameras, and with all-sky cameras, and to take images of the aurora from the ground and to see the substorm begin. And we would see where in longitude the substorm began. And we could say, yeah, those satellites are in the right line or they're not in the right line. And that was our role in Calgary. We worked with the group in Berkeley. We developed with the group in Berkeley the cameras. We developed the capacity to field them and operate them. And I mean, these are very simple scientific instruments. And this is where our stuff comes in, because we're an equal part, I would argue, of a $200 million mission. And the instrument on the left there is the camera that we have 16 of them in Canada. And that camera is $1,500 from an amateur astronomy catalog, and the optics on the front are probably about $5,000. And so for some plane tickets and some cheap cameras and a lot of stress for Emma writing software while she was doing her PhD without being paid, lost, but we have this role in this $200 million mission, and we are still being funded to operate these cameras by the Canadian Space Agency. Emma and I have had way over 100, refereed publications that have come out of this for us, and I mean, I'm sure this.
And well, obviously, there's lots of good information that's come out of it.
Yeah, I mean, it was really a thing that differentiated Themis from other missions, and having this ground-based component and having this visual of the system. And so we've learned a lot. Can
I just ask one quick question here? A couple people are asking whether this sort of equipment in space and/or our satellites, like the satellites in space, if that affects space weather at all. Does the presence of this equipment have any bearing on space weather?
So no, because they're really small. But it's a little bit deceptive. I'll say no, but the fact is there are researchers in the U.S. who are, for instance, developing techniques for cleaning the radiation belts. Oh. And because people have worried for a long time that Russia or the U.S. or some other country would launch up nuclear weapons now and explode them in the magnetosphere. Both the U.S. and Russia did that back in the 1960s. The U.S. experiments were called the starfish experiments. I forget the Russian ones, but they would, like this was the thinking of the day. They would toss a nuclear weapon up, an atomic bomb up, or a hydrogen bomb, and blow it up at 500 kilometers altitude, and then, there's still strontium-90 bouncing around in the radiation belts from those explosions, and so it's really, but now, back then, they knocked the power out once in Honolulu, and, like it was a pretty reckless world back then. But now, if someone were to do this now, they could actually create problem for all of this technology that we depend on in space. And so people are developing ways of using plasma waves generated by a satellite to clean the radiation belt if someone were dumb enough to do this now. It's a serious line of research. And the other thing is that if you look at Jupiter, Io is one of the satellites of Jupiter, and Io is spewing out sulfur, like I don't know if it's a ton a second or whatever. Like it's constantly, this wave of sulfur coming off of Io, and so Io actually makes its own space weather. It's a big thing, right? Okay. And so we could put something up that would affect space weather, but these satellites don't.
Okay, and just another quick question briefly. It sounds as if a lot of countries cooperate when it comes to this sort of research. I don't know if everybody does, but it sounds like there's a lot of global cooperation.
There's no non-cooperance, right? I mean, like this is we go to meetings and we are working with China and we are working with Russia and we are working with the UK and we are working with the US and so on, and it's
that's a comforting thought, hey?
It's fun, yes, and South Korea.
Okay. All right.
So and this is an image that Emma made a while ago, and it's from our Themis all-sky imager array, and it just shows you the aurora over Canada, and this is the biggest scale, highest resolution image of the aurora ever taken, and we get this every night, which is really cool.
Well, except that. So he jokes that Samus taught us that the magnetosphere was big. We learned from all the cameras that Canada's cloudy. This image that he's showing is one of the 2 nights in the history of the project that we had clear cameras across Canada, and it happened to be a geomagnetic storm.
Oh man,
it was the perfect storm. Really,
going to show that you can't control the weather down here or up there.
Yeah, and very, 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 very quickly, you know, we have used Samus, and these are just some figures from a paper that I published in 2008, and we have made tremendous progress on the substorm, and that is actually informing how people are using models to predict space weather, particularly in the U.S. And so it's been a massive success. Now, in terms of space weather, also there's other aspects of space weather than the aurora, and I'm just going to show very briefly that there's this but a program that is the National Research Council, the National Research Council operates at a radio observatory in the Okanagan Valley called the Dominion Radio Astrophysical Observatory, and it is literally, truly Army surplus antennas from the end of World War II that they got for free at NRC in Ottawa. And this guy said, well, what can I look at with these back in 1945? But this is how a lot of science happens, it's serendipity. And he thought, well, I'll look at the sun. And he started tracking the radio flux at 10.7 centimeter wavelength. And he started tracking this, and he was a quirky guy, I guess, and just started tracking it for like decades. And then actually this has become, now it's on the 3rd generation of principal investigator who's running it. This has become the world's most used space weather product, because it turns out that it tracks this radio flux at this frequency, tracks very, very well solar activity, and actually is a proxy for the energy input into the upper atmosphere that causes the upper atmosphere to billow or contract. Right, and so, this was something we didn't know about very well back in the 70s, and that's actually why Skylab came down early, right? Was because the atmosphere was billowing because of solar activity, and it caused more drag, and they couldn't get up in time to boost Skylab back up, and so the U.S. Air Force, and my friend Ken, who runs this, he says, you're important when your computer goes offline, and then you get a phone call at 5 in the morning from a U.S. 4-star general who's yelling at you, where's the F10.7? We need that for our space weather models, right? And so again, this is one of these things where Canada just lucked into, for a few $100 back then, into creating something that is massively valuable for the world.
Well, and it goes to, just someone's asking the question, how widely is the Canadian data and space weather systems used by other countries, and you're kind of answering that question.
Yeah, and overall, I would say that I've been to meetings, international meetings, where I walk down poster hall, and almost every poster from people from all over the world are showing data from Calgary. I've walked down the hall at UCLA on the 5th floor of the mathematical sciences building, and I remember walking down the hall, and every student there had their terminals open, and they were looking at data from Calgary, right? So it's very, very widely used, actually. And I'm just going to skip over this, and and I think what I'm going to show here, these are just graphs of what we call DST. It doesn't really matter what it is. It's derived from looking at magnetic fluctuations kind of averaged over the globe. And when the number is big and negative, we're in a geomagnetic storm, and when the number is small, we're in quiet in terms of the externally driven stuff. And so what I'm showing you here is DST for the year 1989 and DST for the year 1996. 1989 was the solar maximum, 1996 was the solar minimum, and you can see there's a lot of storms in 1989 and basically none in 1996. And it's kind of funny because I started studying this in 98. That's when I started looking at the aurora, and that was still in solar minimum, and I kind of learned all about how I was using the data, and I wrote some proposals and got some cameras and put them out in the field 3 years later, and I didn't understand anything I was looking at because that was solar maximum, and and all the sort of my understanding of what was going on was really skewed towards solar minimum. So
and
really,
quickly, the difference between solar minimum and solar max is just the level of activity?
It's the sun, the output of the solar wind, basically the energy in the solar wind and the impact of the solar wind.
So maximum means there's more?
More, just faster, denser,
Gotcha.
more dynamic, and then there's even this, people studied a time period which was back in, I forget what year it was, but there's a special issue of Geophysical Research Letters, which is on the day the solar wind went away.
Now, is that the same? Now, someone is asking a question. When another big peak in the solar flux hits in the year 2020,
Yeah.
that's what we're talking about,
Yep.
solar flux? Okay, so this person is asking what can we expect to happen, which maybe get a little bit ahead of ourselves.
Well, we can expect there will be more magnetic storms. Every solar maximum is different than every other solar maximum. It's not a perfect cycle, but you can expect a lot of action, a lot more aurora down at lower latitudes. I got a call from people in Yellowknife because they were getting worried because we're coming into solar minimum, and they were thinking, what would that mean for auroral tourism? And what that means is that there'll always be aurora over Yellowknife, and if it's really quiet, it's not visible from Edmonton or Calgary or Winnipeg, right? And so it's actually not that up there, right? But when you get these big events that you see down here in Calgary or Toronto or the one famous one that happened on Halloween in 2003, where my friend in Montana said the aurora is coming, and he took his family outside, and they watched the aurora come over the northern horizon and went overhead, and then went over the southern horizon and disappeared. And people saw it in Mexico that day. And so that's the kind of thing we hope for, but it also is the kind of thing that plays havoc on space weather.
Okay, which we're going to hear a little bit more about.
Yeah, so I think at this point in time, that's a slide I don't recognize, so that's Emma's.
Yeah, which is a great segue from space weather over to you, Emma.
Yeah, well, so Eric's been talking about the ground and what you see in the aurora and that aspect of it, but in space weather, there are effects when you're actually in space. And so this is a plot. What you're seeing here is a plot from a geosynchronous satellite operated by Los Alamos National Laboratory in the U.S. So you're looking at particle fluxes. And so you can see that at the beginning of the plot, they're relatively calm, and then you can see this havoc.
There's just stuff moving.
Stuff starts moving around, and you end up with a lot of flux. And that's associated with what Eric showed earlier with that all-sky image where the aurora got bright over a matter of 2 minutes. When you're actually sitting in your space, what you would see is something like this, where all of a sudden you're at a satellite and you've got a wash of high-energy particles that are rushing over you. And this is an enhancement in the local plasma population, or the particles that are in the space environment. Now, those particles, once they are injected, and this is a little bit of a complicated figure, I apologize, but they get injected, and that's what we call this an injection, a substorm injection. And once they're in the system, they start to drift due to the physics of the inner magnetosphere and the motions of particles in magnetic fields. And you can watch these particles drift around and around the Earth. And you can actually see in this figure on the bottom, you see what we would call, this is the rise in flux at the bottom, you can see a drift echo. And these particles can actually live in the near-Earth space environment for quite some time. And they can execute many orbits before they start to decay. And this population of particles that are sort of this internally driven dynamics that Eric was talking about before can actually become a seed population for the radiation belts, the higher energy particles. And this is how you can make a set of particles become what we would call space weather active. Once you're into the radiation belts, you start to become a hazard to the satellites that are in there. And Eric and I are involved in a project right now for a UV imager, and one of the things we don't want to do is we don't want to go through the radiation belt. Because when you start to put a satellite into the radiation belt, those particles are so high energy, they're moving through the spacecraft.
Wow.
They're not stopping at the spacecraft, they're going all the way through. And that can cause havoc for, power systems, anything.
And degrade detectors.
Yeah, so for us, it's degrading the detector or blowing up the high voltage power supply. But this is a figure that I stole from NASA that just talks about the space environment hazards that you have from a satellite that sits in that type of environment. Now, the nice thing for us, I mean, back to the aurora again, those high energy particles, when they do hit the upper atmosphere, they're not, I mean, they're causing visible aurora among other things, but they're so fast when they hit the upper atmosphere, they're stopping at the upper atmosphere and they're causing X-rays. And you think of the aurora as a visible phenomena, but when you get the energy high enough in the aurora, you actually get X-rays. I mean, we don't see them from the ground because they're absorbed by the upper atmosphere. But if you're in space, and this is an image taken by an astronomy satellite, actually, Chandra, and then there's actual X-ray aurora that you can see from space.
Does that affect you if you're in an airplane over with northern lights? Is that?
I don't have an answer for that one, but I think the larger issue is from high energy particles that get down to the altitude of the planes. You know, and so you can get a radiation dose if you're on a transatlantic flight, which is equivalent to a chest X-ray. And this is actually a significant space weather issue because airlines divert planes out of the auroral zone when things are very active, not because of the passengers. I mean, I won't say they don't care about the passengers, but it's the crews, the flight crews. So if you're on a transatlantic crew and you go through 10 of these events a year, you've exceeded the occupational safety level for radiation dose, and so that's big money.
And this is sort of the higher energy component of the aurora. So we're talking about the lovely visible part of it, right? But there's that higher energy,
the X-rays,
which I would call the space weather. Part of the aurora. So the other thing these particles do when they come down, and there's another X-ray image of the aurora up there in the top left, that's from a little further away. But once these particles, if they're very high energy, they can start to get down to when they're hitting the upper atmosphere, they have more energy, and so they're penetrating deeper. And if you can get down to certain regions in the upper atmosphere, you can actually affect the way that high-frequency radio waves propagate. And that has consequences for, among other things, like radio wave communications with airplanes or naval ships. This is from, I think I took this one from the U.S. Navy, this figure at the bottom here. And so you can actually have a significant effect on communication ability when you get those particles into a region where they can affect technology. Now, the top figure here that I'm showing is from NOAA, the U.S. NOAA Space Weather Prediction Center. And when we talk about radio wave frequencies, this is a map at the top where they've got the frequency that's affected in radio waves. And they actually produce this as one of their space weather products, where they actually communicate to the global community what radio waves are going to be affected by the precipitating particles.
Is that like a daily, like a weather forecast, like we listen to?
Yeah, they have models, real-time.
But it's not prediction though, right? Like they do predictions, but we're not good at predicting now. We do what they call nowcasting.
Yeah.
Okay, so like information that is like,
This is a nowcast product. They do have a prediction aspect of it where they say that they anticipate radio blackouts, for example, if the sun lets out a radio.
Oh, interesting. So there's a lot of industry behind this.
Yeah, I would say there's a lot of industry behind this. But this right here, this is just sort of looking at the types of radio frequencies that are affected. And on the bottom, this is our claim to fame, which is the scientific instrument, which on the left at the bottom looks like a fence. This is our scientific tool for monitoring the same radio waves. And if you see the plot from the instrument is over on the bottom right there, what you've got is 3 days of data, and in the radio frequency, what we're seeing, those peaks and valleys, that's the rotation of the Earth sweeping through the center of the galaxy. And so what you're seeing is the center of the galaxy, and then you see those blips where the signal goes away. That's where those high energy particles came down and they disturbed the upper atmosphere enough that they changed the atmosphere's properties for radio wave propagation. And so that signal that we were seeing coming from the center of the galaxy went away. And that's our own scientific observation of the radio wave sort of blackouts or attenuations.
Okay, we have a question here that's, this might be a good time to ask it. What are the chances of the solar wind or the space weather coming down to the Earth's atmosphere, if any, down to Earth?
Well, so the solar wind, you know, if you look at the magnetosphere, the magnetic field lines in the magnetosphere that are in, the aurora has that oval, and in the center of the oval it's dark. And those magnetic field lines are actually connected directly to the solar wind where it's dark. And solar wind plasma is coming down those magnetic field lines and raining down. We call that polar rain. In that dark, we call it the polar cap. And they are very low energy, and they do almost nothing, right? So the solar wind, one of the interesting things about the aurora is the solar wind, the plasma in the solar wind is very, very cold and low energy. And the electrons that are hitting the upper atmosphere in the aurora are, in solar wind, they might be, 10 electron volts. But when an electron hits the upper atmosphere in the aurora, it might be 10 kilovolts or 10,000 times or 1,000 times more energetic. And that's one of the big mysteries in the aurora is what gives those particles that energy. But the solar wind is coming down in the polar cap, and it's not doing anything. And the larger thing that the magnetosphere protects us from are high energy cosmic rays. Right, so the solar particles, generally speaking, aren't a big deal, but they provide, again, this energy for the whole system, but they don't really matter beyond that.
Let me ask one more question here before we get back to the radio waves, Emma, if I may. What sci-fi movie / book / game gets space weather right? Are there any out there?
Well, so it's not
the
core.
Not the core and not the frequency. And
I just saw Passengers on the plane the other day. That was,
I haven't seen that.
So nothing comes to mind.
No,
there's no story participant. There's no
handy-dandy
movie.
We flaw in pretty much anything because we're ingrained in it.
Yeah, but I think it's worse than
So don't trust the movie.
There was that the day after tomorrow, the weather one, like
that
thing. Well, they did a survey of people coming out of the day after tomorrow, and the British Scientific Organization, and it turned out that people who saw that were more concerned than they were about climate change, but they knew less than before they went in the movie.
Okay, well that's a good tip though. So don't trust Hollywood with the space weather. Okay.
Yes.
Okay, Emma, please carry on with your slides. We'll get to some more questions in a few minutes.
Yeah. Okay, and so when I was talking about those drifting blobs of particles that you inject this plasma into the air space environment, one of the things we can actually see it from the ground as well. And so this plot here is just showing where we see these injections, and we don't on the ground tend to see it multiple passes. It doesn't tend to drift. We don't get multiple drift echoes, I would say. By the time it comes back, it has drained itself significantly, that it's a population in the magnetosphere, and it's not providing that high energy aurora anymore. I can just skip one. One of the other effects from the radio wave side of things, once you start to deposit significant energy into the upper atmosphere and you create structures in the upper atmosphere, you can start to have an effect on the GPS signals. Because of course, when you have a ground-based receiver, your position is provided by it's the solution to a set of equations where you have 4 satellites, a minimum of 4 satellites that are providing you a signal, and then based on that you can triangulate your position. But those signals have to come from satellites, which then have to pass through that region where we have this radio wave disturbance. And so there's been a lot of, if I can click forward to the movie, try and see if this plays, hopefully it plays for most of you. There are times in which the aurora can disrupt those signals or provide modulations on those signals. It's called scintillation. And it basically changes the property of the signal as it goes through the upper atmosphere. And if you are a high integrity user where you require centimeter accuracy, you may experience some difficulty with the signal and the positioning. I mean, I'm not being alarmist. Please don't think that your car is going to drive off the road or anything like that because there's aurora overhead. What we're talking about is minor effects right now. The engineers have solved most of the aurora problems, I would say, for the majority of users. But if you're a high integrity user that requires centimeter accuracy, you may have to think about space weather effects.
Like doing that, and that could be ships navigating narrow canals and stuff like that. And so high stakes stuff. And 25 years ago, space weather was a big problem for accuracy in GPS. And then the engineers have kind of got all that under control. Yeah. But now what's happening is GPS has gotten so accurate that they've actually gotten down to centimeter scale accuracy, and now those effects are popping up as an issue at that level.
And no doubt teams of engineers are on figuring that one out as we go.
Absolutely.
Yeah. It's one of the research. It's one of the research lines that we have here at the UC is actually the next line is what we're trying to do on that avenue is use the auroral information and the scientific receivers that are used for GPS, where it's not correcting itself. It doesn't have those fail-safes in it like a commercial receiver would. But if you remove all of that and you can actually see the disturbance on the signal and you don't let the receiver correct itself, for example, we're using the auroral information in conjunction with that to try and figure out where receivers would have trouble, what types of receivers would have trouble. And we're working towards sort of an advise and monitor situation where we could advise a GPS user, a high-integrity GPS user, of where the effects may be a factor for them in a statistical sense. And that's one of the lines of research that we have here at the UC. And this is the same type of thing, or the same type of procedure we would use for when I spoke about directional drilling earlier, because with each one of these disturbances comes magnetic disturbances. And if you're in the drilling industry, one of the key drilling practices now is directional drilling, where they're using the local magnetic field to orient where they're drilling. And you can imagine if you all of a sudden drastically change the magnetic field through a magnetic disturbance that happens to be of space weather origin, you are no longer quite certain where you're pointing, and you continue to drill. There are companies out there that deal with this, and I monitor and advise, again, kind of scenario where you shut down drilling for an extended period of time to allow the disturbance to dissipate. And those are the types of scenarios where we can use, or the science can help feed the industry practices.
We had a question earlier. I'm just trying to find it. Somebody was asking about sort of the effect on economies. Do we have a dollar value to what, or a dollar guesstimate of what this might?
So the British.
Yeah, well, the British government has identified space weather as one of the 7 top hazards to their economy.
Wow.
And there's not a dollar value on that. There's dollar value estimates for catastrophic events, which we've not had in the space age. Right? We've not had, there was a magnetic storm back in 1865 that if it happened now, people think could knock out every satellite in orbit at once. And that, you can't even estimate what the dollar value of that is, because it's not the value of the satellites. That's how we move currency around. That's how we move information around the globe. I mean, we are using space as we speak. We are using space all the time. It's woven through the fabric of our economy. But there are people in the U.S. and companies don't like to talk about this. So I'm going to be careful what I say about this, but there's a field of study in the U.S. where economists are looking at the impact of space weather, for instance, on power generation companies in the U.S. because it turns out when the sun is more active, profits go down in companies that generate electricity, and they don't. And so they don't. It's not a big deal, but it's money and for these companies and their investors, and it's costs that are passed on to consumers. And so people are starting to but you have to be really careful about that because and that's why people are teasing out of big databases now, using sophisticated analytics and understanding kind of how this affects the economy. And so there's going to be a cost for airlines when it's space weather.
Right.
But getting them to admit that is very difficult, right? So I don't have a direct answer to that question.
Okay, no, that's all good information.
No, and I think
so
we're actually on the topic already.
Oh, I love it when that happens.
Yeah, so basically, we're finishing off with some slides, some screen grabs that Emma and I took off the web. And this is one of the things that's kind of nice about one of the things that's fantastic about the way the world is now is that, people have access to almost all of this information and in real time. And if you Google space weather, if you go to NOAA, to the NRCan site, to our webpage in Calgary. And so just showing here, this is the Facebook page for the Alberta Aurora Chasers. I love this group, right? And they post pictures of the aurora, but they also post a lot of cool information. And you can tell if it's space weather active right now by going to the Alberta Aurora Chasers, because they're all of a sudden posting pictures from southern Alberta, right, or Montana, and in real time, which they can do because of how interconnected we are. And so I highly recommend actually poking around. This is the Aurora Australis Tasmania Facebook page, which has 75,000 members. Okay, and they are again equally as excited about the aurora as the Alberta Aurora Chasers, and I mean these are really fun groups. And then this is the Canadian Space Agency. It's a web page they have for a project called Aurora Max, which is actually Emma's the principal investigator on, and that's where we have a camera in Yellowknife that's an all-sky imager and takes HD images, magazine quality images, and puts them on the web in real time. And that actually the CSA had to increase their web bandwidth when Aurora Max kicked off because there were so many users all over the world who were looking at this. And
well, why do you think that is? Why are people so fascinated with the aurora? What is it about the northern lights that just?
I mean, it's really beautiful, you know. I mean, it's something that a surprising number of people have on their bucket list. Like, you know, I want to see the northern lights, right? And it's a sort of a spiritual thing when you experience it. On top of that, it's woven through our culture, certainly in Canada and other northern nations. You know, I mean, if you look at travel posters, or you look at literature, you know, you look at stamps, you know, I mean, people are into it. You know, and I mean, it's like, why do I find this beautiful? I don't know. There's not an answer to that question, right? I mean, I can tell you that all of the thinking about it has not taken a shred of the joy of when I see it out of this, right? And I've never, yeah, I think I told you earlier, Jennifer, that you know, I was on a trip up in Alaska and at a conference, and we took a bus outside of town, outside of Fairbanks, and I was with, you know, like 100 auroral scientists from around the world. And I was standing there, and there's this one group talking about, oh, yeah, well, those electrons are doing this and everything else. And I was like, I'm going to walk away from you, and I'm going to stand out in this field, and I'm just going to look at this and take this in, you know. So this is another thing called Aurora Watch, which is a project up at the University of Alberta where they look at the magnetic fluctuations at a magnetometer just outside of Edmonton, and they send out alerts. They send out email alerts to people who sign up when they think it's going to be good aurora watching in Edmonton and around that. And the nice thing is, you know, so this is the Natural Resources Canada, Space Weather Canada page, which tells you this is really industry oriented. This is for people like the directional
drillers
right.
That utilize this kind of tool. You know, so.
And I think we have all these resources listed too. Everybody
Yeah.
who's listening, you can click on the resources link and find all these as well.
Yeah, and then just to round it out, there's the NOAA, the National Oceans and Atmospheres Administration in the U.S. They have a space weather page in the dashboard, and you can kind of set it up for what you're interested in. And they have models that they use data and models to try to say where they think the aurora is now. And then, you know, if you go forward, you can look at this webpage that actually Emma built back in 2007, and it looks at our data in real time. And so you can see the images from our Themis array, or from our other cameras too. But this one is the one that's most sophisticated.
You took the picture when there was no.
Well, yeah, sorry, yeah. Well, but you know, that's what it would look like if you went there right now, because it's bright over all of Canada. And so you can just kind of go through this. And I think you know, for people, it's really kind of fun to be able to do all of this in real time. Mm-hmm. And then we'll just round out. Do we have time for a couple more slides? Or should we wrap it up?
Sure.
Okay,
yeah.
two more slides.
Yeah.
I got a couple more questions for you too, but let's.
Yeah. So one of the things, if we're looking at space weather and moving forward, and what is research going to bring, this is one of the, or actually the mission that was selected out of the European Space Agency and Chinese Academy of Science mission proposal call. It's called SMILE, great acronym for a satellite mission, or Solar, Wind, Magnetosphere, Ionosphere Link Explorer. And the idea of SMILE is to actually look at space weather, and that is look at the connection between the solar wind driving the magnetosphere, and then look at the aurora at the same time. And Eric is actually the PI of the UV auroral imager that will fly on SMILE. And the image I'm showing here is an artist's rendition of the orbit, and the idea is to get that spacecraft high up, very, very high up. It turns out to be about 19 Earth radii away, looking back at the Earth to take pictures of the aurora in UV, and at the same time imaging where the solar wind meets the magnetosphere. And so you can look at the signal that's coming and the power that's generated at that interface, and watching the space weather effects in the aurora. And now this is another artist's rendition of the spacecraft looking close. But the idea is for us to image in the UV. And one of the nice things about the UV aurora is that in the UV, you can separate out the day glow of the Earth and the aurora. And so we can actually see the aurora. It's not just a night side thing. It's not something that you just see at night. You can see it all the way around the Earth, and even on the day side. There's probably aurora above us at some point right now, a little bit north of us. but there would be aurora during the day. You just can't see it because the sun's really bright. But looking back in the UV, we would be able to pick out that global distribution and look at how the effects on the boundary with the solar wind and the magnetosphere, how that solar driving force is actually driving the space weather.
Yeah, and the thing that we're looking at, is actually we've created a time series of the size of the aurora oval, and that's why we have to see it at all local times. See it on the day side, and that's the thing. That time series represents the thing that powers space weather, and our field has never created that time series, and so we in Calgary are going to do that, and we're going to be famous.
I've got two quick questions. I want to ask each of you one question before we go here, because people are asking us. One is, does space weather, a lot of questions out there about space weather, does it affect our temperament? Does it affect biological life? What effect does space weather have on those of us walking around on Earth?
Well, so I saw a study, it was last week I think it was, about a set of whales that were going up the coast of Finland. And they hadn't realized that whales use magnetic navigation until they found this set of whales trapped in a bay somewhere in Scandinavia. And then they traced back when they would have been caught, and they worked it back to the recent storm that we had, the geomagnetic storm, is right when they would have been passing this inlet, and they
took a wrong turn.
And they took a wrong turn and got caught somewhere they never would have been. And so I think almost certainly space weather does affect biology. Yeah. And certainly migration patterns.
Okay.
I don't know about us. I don't know.
No, we'll check back with you on that one.
In a few decades, we'll get to that.
Obviously, there's a lot of work to be done. And Eric, I wanted to ask you quickly, does the northern lights, does aurora borealis have a sound? Does it make a sound? Someone's asking.
So, I mean, the scientific answer to that is no. The answer to that is maybe. There are a lot of people who, from a lot of different places around the world, who have no connection with each other, who report compelling stories about what the aurora sounds like. And it's not all people, it's maybe a third of people or a quarter of people claim to hear something when there's bright auroral displays. And so I'm inclined to say yeah, but don't tell my scientific colleagues that, because I'll take it credibility hit.
All right. I think we have to leave it there. Thank you both very much. Before I let you go, I was hoping you could give us a couple of sort of takeaways that people that you can give to people before we wrap it up here today about your research and about the aurora and about space weather.
I'll say, I mean, space weather matters. Don't lose any sleep on it. Over it. It matters. It has impact, and that I feel fortunate to be able to study something that is so beautiful, and we as Canadians should feel fortunate to have this kind of lock on this globally.
I just think Eric said it all.
Well, it sounds like there's a lot more research that's happening now. You just mentioned SMILE, and there's a lot of research everywhere, so it's certainly something to keep an eye on over as you say, over the decades, because there's going to be more information coming.
Absolutely.
Well, thank you both very much. I know we didn't get to all of your slides here, Emma, and I apologize for that. And we didn't get to everybody's questions. I also apologize for that. There's so much information here today. We couldn't quite get it all in, but I think it just shows the interest that people have in the topic. I ask everybody again to just take a second to fill out our survey that we have there. As I mentioned, Eric and Emma talked about a lot of resources for those of you who want to learn more about this. They're all listed in the resources link there, so dive in and learn more. Go to Facebook, join those groups. You'll have beautiful pictures in your Facebook feed every day. I can attest to that. Please sign up for other UCalgary webinars, download our ebooks. We've got videos, we've got all kinds of representations of our scholars' research, and you can find it all there at that website. So take a look at all of that. And join us again next week for tips for future Mars dwellers. That's on October 17th. That's going to be a really interesting one as well. And then if you were wondering about solving the mysteries of the quantum world, we've got you covered October 24th. So please come back and see us then. If you have ideas for other webinars, more things you'd like to learn about from our researchers, give us an email there. And thank you all again for joining us today. My name's Jennifer Alford, and we'll see you next time.